if you've had a chance to look at your textbook, they go into a ton of detail with some of this atomic theory, way more than what the AP exam requires. They really scaled this down quite a bit to the two most important equations that deal with atomic structure. One of those being the frequency times wavelength equals speed of light. The other one here is used to measure the energy of a particular photon. So here Einstein's experiment was telling us that these different photons or packets of light contain different quantities of energy. And Max Planck kind of summarized that into an equation. If you're really interested in this, you can read more in the textbook. But again, if you have read the textbook and your mind is ready to explode, don't worry about it. The book goes into way more detail, but some people are kind of interested in some of this atomic theory, which again, this was kind of scaled down quite a bit when the AP exam was just restructured. So previously we thought that matter could emit light, it absorbed light in any different quantity, any quantity of energy. But Planck was studying incandescent, which is light emitted from different sources. And he noticed that the energy may not be emitted in a continuous range, but in these discrete amounts. And these experiments led him to hypothesize or postulate that these amounts of energy, or these packets, or these photons of energy contain different whole number integers of energy, different quantities, but they all seem to be consistent around this particular whole number integer. So again, it's not that these photons can just have any amount of energy. They seem to contain specific quantities of energy, and that energy can be calculated using something called Planck's constant. Energy is gained or lost in multiples of this Planck's constant times the frequency. Interesting. So this equation, this one down here, this is used to calculate the energy of a photon. So again, we're still thinking about this idea that energy is quantized. We don't have electrons that just fly all over the atom wherever they want to. They're in specific energy levels. And when they move up and down the energy levels, they're only gaining or releasing specific quantities of energy. It took specific quantities of energy to remove electrons from the surface of the metals in that photoelectric effect. Or here, Planck's data suggests that, again, these photons contain specific quantities of energy, and they all seem to revolve around this quantity 6.63 times 10 to the negative 34th joules per second. And we're going to multiply this Planck's constant times the frequency to calculate the specific amount of energy in a photon. So again, energy is quantized. It's absorbed or emitted in specific amounts. And when we talk about energy, now we're talking about it containing specific packets or photons. So again, those photons contain specific quantities of energy. This is the second equation that's given in the AP packet in this atomic structure section. And again, they will give you Planck's constant. They'll tell you what all these variables stand for, so you don't have to memorize any of this. Planck's constant in your AP packet is actually just a little bit different. They'll list it as 6.626 times 10 to the negative 34th, and then they have it as joule seconds, which is fine. So again, this may be the number that's given in the book, but if you're doing homework, get used to looking at the AP packet and use this 6.626. Obviously, I wouldn't take off points if you didn't, but if you were taking the test, that's the number you're going to look up in the AP packet. Joule seconds. All right, let's put this thing to use. Blue color in fireworks. Sounds fun. Is often achieved by heating copper compounds. So you might remember that copper compounds usually either burn kind of like a blue or green color in a flame test at 1,200 degrees Celsius. That's hot. That's why we don't play with fireworks, right? The compound that emits blue light having a wavelength, oh, boogers, of 450 nanometers. How much light is carried by a photon of blue light? And what about a mole of photons? Okay, so here's the equation that I eventually want to use. E, delta E, change in energy equals Planck's constant times the frequency. Just kind of that Greek symbol nu. Okay, so I know Planck's constant, I can look that up, but I'm not given the frequency, I'm given the wavelength. Good thing we can calculate the frequency. Here's what they'll often do on an AP question. They'll try to kill two birds with one stone. Here's the other equation. Speed of light equals frequency times wavelength. Oh, so we might have to calculate the frequency, and then we'll use that in the second equation to calculate the energy of this photon. So again, I look up all these equations in my packet. They tell me all the variables. They tell me all the constants. The speed of light, 2.998 times 10 to the 8th. And I'll write it just like in the packet. Meters per second. They have it listed kind of like this. Speed of light equals frequency, which I want to solve for, times the wavelength. Now, unfortunately, the speed of light is given in meters, and my wavelength here is given in nanometers. So we're going to have to make that switch. So you got to do a little sidebar. 450 nanometers. Let's see, we could set this up as 1 nanometer is 10 to the 9th meters. Or you could say 1 meter is 10 to the negative 9th nanometers. Either would be totally fine. Oh, whoopsie, I got that flip-flop, don't I? Hello. Get out of there. This would be 10 to the 9th. There we go. 10 to the 9th nanometers. Or you could go 10 to the negative 9th meters is 1 nanometer. Either way, this is going to come out to be super, super tiny. Let's leave this as maybe 2 sig figs, because again, there's no decimal spot at the end. So I think I'm going to leave it as 4.5 times 10 to the negative 7, and now we're in meters. So I can solve for the frequency. Let's go 2 sig figs. 6.7 times 10 to the 14th seconds to the negative 1, or you could just use an S for seconds. Now, if you find that you're not getting that number, you're getting something kind of wild, watch the way that you plug this in your calculator. With scientific notation, if you're obsessed with using that caret key, so if you're going like 4.5 times 10 caret negative 7, you're going to want to put that in parentheses when you plug it in your calculator. Otherwise, your calculator doesn't do order of operations correctly. Your other option, your better option, is just you use that exponent key, that EE key, which is specifically designed for scientific notation, but just don't put times 10 in there. So I would plug that in as like 4.5 EE negative 7. That EE means times 10 to the what? And then you just tell it the exponent. So now that I have the frequency, I can use the other equation. Delta E is what I'm looking for, the energy of the photon. Planck's constant is given in my AP packet. 6.626 times 10 to the negative 34th joule seconds. They just have joule S. I'll put a little dot in there. Joule times seconds. And then here, watch what happens with the units. We plug in the frequency, 6.7 times 10 to the 14th. You could say S, seconds to the negative 1, SEC. Everybody's going to know what you mean. This kind of makes sense. With units, seconds are going to cancel. So when we talk delta E, we're looking for some unit of energy. It's going to be joules. So I plug this in my calculator. Let's leave 2 sig figs here. So let's say delta E is 4.4 times 10 to the negative 19th joules. And now that's joules per 1 photon. Now you don't have to say joules per photon. If you just leave it as joules, that is perfectly acceptable. But now the last part of this wants to know how much energy would be in a mole of these photons. So then I'm going to take this guy and multiply by Avogadro's number, which again is given to you in the AP packet. And don't shortcut this thing. It's given as 6.022 times 10 to the 23rd, and that would be like particles per mole. So if I plug this into my calculator, I'll get joules per mole. And again, let's just go 2 sig figs. That should be plenty. How about 2.6 times 10 to the 5th? And let's see if I can squish that in here. This would be units of joules per mole. Per mole of photons. See, that's not so bad, but that's kind of a typical type of calculation that they may give you. That's killing two birds with one stone. It's using both of those equations that are given in the atomic structure section of the AP packet. And again, there are other equations that are given in the book, and they're very interesting. And if you ever want to talk about them, I mean, we can like calculate the mass of a photon. Whoa, are you telling me that blue light carries mass? Now that is going to give you a headache. Stop by sometime and we can definitely talk some advanced atomic theory here. But these are the only two equations that you need to be familiar with for the AP test. There we go. They really did make this section much more manageable than it used to be.